Okay, I've had some technical difficulty, and I am not going to talk over the rest of that. Solar eclipses only occur at the new moon. We've talked about the different types of eclipses, and we don't see them at every new moon and every full moon because the moon does not orbit in the plane that the Earth orbits in. There's a slight tilt, about 5 degrees. And that means we have eclipse seasons. There's times when the lunar eclipse can occur because the moon happens to be in the plane of the Earth's orbit at the same time as it's in the Earth's shadow. And we have solar eclipse seasons. This is a cyclical effect. Sometimes the shadows are just out of place. They're just not striking the surfaces. So we have eclipse seasons each year. And the conditions to have an eclipse, it has to be a full moon for a lunar eclipse or a new moon for the solar eclipse. And it has to be one of those places where the orbit of the moon crosses the orbit of the Earth, the ecliptic plane. And so that leads you to a cycle. And the cycle happens to be 18 years, 11 and 1/3 day for solar eclipses. And so this map that I've put in here shows those cycles, what's called the Saros cycle. Now the type depends on basically where you are and and how the Earth has moved in the intervening time. But effectively, these you can kind of see what's happening here. Here was the 2017 eclipse. If I turn on the pointer, and here was the 2017 eclipse that we saw. Um, and at some point in the future, there'll be a copy of this occur. But because of this 1/3 of a day, it'll occur about 8 hours. And so instead of occurring over us, it'll occur over Europe, and then it'll occur over Asia. And so they shift over time. And then there are other ones. We can see some that occur here, and they will shift over some. We can see the remnants of one there. And there's some in the southern hemisphere. You can see those. So there's several different sorts of patterns, and they shift around because this extra third of a day causes. But they do seem, there should be another one that follows roughly the same path as the 2017 one, and it should be in only about 57 years. We all live long enough for that, I hope. There'll be other ones that you can see or go travel to. Right? There's going to be one in about 3 or 4 years that will start on land in Mexico and rise up through Canada. So we'll get to see that one at some point. There's not a whole lot of total eclipses over us, unless stuff shifts around just so. Right. So we look at the night sky and it's pretty well explained. We have stars, we have galaxies, the Milky Way. We can map our way around through it. We understand why seasons occur. We understand why eclipses occur and phases of the moon. But we have the benefit of thousands of years of astronomy and hundreds of years of astronomical research. They didn't have that. So there's a lot of mystery. If you look in the night sky, you can generally see 5 planets. 6 if you count the Earth, because you can generally see the Earth at night. Mercury and Venus tend to be very near the sun. Sometimes they rise in the morning, sometimes they set shortly after sunset, but they tend to be very near the sun. Mars, Jupiter, and Saturn tend to be in the night sky. You can typically identify them. Jupiter's very, very bright. Saturn's fairly bright. Mars is a fairly red object. Venus should be about the brightest object in the sky that isn't the moon, which tell what that is, or the sun. Mercury is going to be hard to see. It stays close to the sun. but you can see it. And here's a picture. We got all 5 of them in the picture. There are some other stuff you can see. Uranus, you can see with binoculars. Neptune, maybe with a small telescope, maybe with binoculars. Um, Things like Pluto and the other small planets, you need a good telescope to see. But we're talking about essentially people in the ancient world observing the planets. They saw something unusual. Stars always rise in the east, set in the west. But planets, from our perspective, they're always going to rise in the east, set in the west. But they change their position. It's obvious that they're orbiting something, like either the Earth or the Sun. But sometimes they appear to move backwards. So in the sense that when we see the stars start rising and then they always rise later and later and later and later. They always shift night to night. They always move eastward, which means that they rise later and later. Sometimes the planets rise earlier, which means that they're moving west relative to the stars. And this is what we call apparent retrograde motion. Retro means it's moving backwards. There's also the word prograde, which means moving forwards. So this is what we call retrograde motion. Um, and so from our modern perspective, it's really easy to explain. The Earth is moving. So when the observer moves and the observing moves, you can get these effects. It's like passing a car. You start behind it at point 1 in this image, and when you catch up, you're at point 3, point 4, point 5. That's when you pass, and then you're ahead of the car, and so the motion continues on as usual. And so if you're seeing this sort of circular motion, there are points where you're gaining on, the Earth is gaining on Mars, let's say, faster than it was before because it's actually moving along its path. It's not moving, the Earth is moving at 1, basically perpendicular to Mars's orbit, and at 7 perpendicular. And so we see the motion of Mars as it should appear. But at points at 3 and 4, we're moving extra fast. And so it looks like we're catching up. And that looks like Mars is moving backwards because we don't observe our own motion. So it's easy for us to explain because we know the Earth's moving and we know we're just lapping a planet or another planet's lapping us because the planets are all moving at different speeds. But if you think the Earth is standing stationary, that's hard to explain. And there was no concept that the Earth might be moving because you couldn't feel it moving. The fastest you could feel anything moving, probably about 20 meters a second. Because we're talking about horse-drawn carts or ships or falling off of something. So it's hard to imagine anything moving. It's easy to put the Earth at the center of the universe, and then you're seeing stars move in the sky, and some of them, the planets, move backwards. And obviously, the thing that they did was they attributed it to their mythology. But there was some attempts that we'll get into in chapter 3 to explain things scientifically. And they even considered that the Earth moves. They rejected the correct explanation because they weren't able to observe everything that they wanted to, that they needed to understand that the Earth moved. So from our perspective, we nearby stars relative to the fixed stars. And this is a problem of technology. In the ancient Greeks' time, they had to do naked eye observations, and this lasted from the beginning of recorded history up until about 1830. People observed the sky with their eyes. Galileo will talk about in the telescope, but until about 1830, no one could measure the motion of nearby stars. And so what happened? If you're listening to this, what I want you to do is hold your finger out at arm's length, close one eye, and then open it and close the other. And you should see that your finger appears to move in your vision relative to the background you're looking at. Like if you point at an object in the room, like if you have a clock in your room, point at the clock and then alternate which eye is open and closed, and you see your finger moves. And that's parallax. So what's happening is in your eyes are at different positions. And so which eye is open changes the position you see. You see one image at one time and then another image at another time. So on Earth, it's really hard to do that in space. Like we can't measure parallax by moving along the surface of the Earth. But what we can do is wait 6 months and see if the stars try to move. Now you can do this with a telescope. You can measure parallax of nearby stars relative to far away stars. But the ancient Greeks, all they could do is look at the stars and see that they appeared fixed. Because the best you can measure of this sort of parallax, the angular changes that you can measure is about 1 minute of angle. And the size of the parallax is on the order of 100th or 1,000th of that. So it's just not measurable by eye. And that leads to two problems. We have this parallax that can't be seen and the retrograde motion that can. And we need a theory that explains why both of those are true. And there's two consequences. One is the stars are very, very, very far away. The second is that the Earth doesn't move. And so there's no reason why we'd see parallax 6 months later. And so there were people that considered the stars were far away and even tried to come up with a measurement for them. But generally, as the Greeks developed their model of the solar system, they decided that the stars could not be that far away. The Earth didn't move. And that's going to lead us into chapter. We're going to talk about the development of astronomy as an ancient observation to a science and into the Renaissance. So that ends this. That is your night sky. So this is 2 videos. I had some technical issues with the videos, obviously. I'm still recording. But I will go back through these slides and the places where you need to do a calculation here, angular size, I will make sure that you see a third video that is specifically how to do this calculation. That's what I'm doing tomorrow because it's midnight and I got to go to work tomorrow. So I hope y'all enjoy these. Something else that you would like to get out of these, or maybe you would like to have a jigsaw session or something like that where we talk about astronomy, please let me know. Let me know when a good time would be, or if you want a different way of seeing this, and we will look into that. Anyway, that concludes the video.